This is a guide video for worksheet number 5. I'm going to go through much of it explicitly, give you answers. So if you follow along, you'll get much of it already done. The rest of it, I'll give you pointers. Hopefully walking through those examples will help you complete the rest. If you're still having trouble on the parts that we don't go through in a lot of detail, you're welcome to make an appointment with me. We can meet up via Zoom, or you can log on to one of the regular Zoom sessions. I'm happy to give you more help and walk you through those others if you need it, but try and work through it and do it on your own. Okay. So for this first problem, which should be somewhat familiar to you, we've done problems like this before. You are given genotype counts, and you are asked to calculate some values for the population. The first is the genotype frequencies. Now, genotype frequencies are really just a stepping stone to getting to the allele frequencies, the P and the Q value, which is what we're really after. And there's another way to do it, which I'll walk you through both ways. I actually prefer the second way. I think it's a little easier for most people, but whichever way you prefer. So to figure out our genotype frequencies, all we do is take each of the individual genotypes and then divide by the total number of genotypes that we've sampled. So we would do 40 divided by 240, 80 divided by 240, and 120 divided by 240. And so we would get values out. And there's some rounding error here. That's one of the reasons why I like the second one. It's a little easier, I think, to do mathematically, but whichever you like. So about exactly a sixth of the population should be big A, a third big A, little a, and then the remaining half should be little a, little a. Now, if we want to figure out our allele frequencies, the mathematical equation for this is we take half of our heterozygotes, and then we add in the homozygotes, and that gives us our p-value. And if we take half of the heterozygotes and then add in the other homozygotes, that gives us our q-value. So half of 1/3 is 1/6. We add that to 1/6, that's 2/6, or 1/3, 0.33333. So that is our p-value. Same thing. We do half of 1/3, which is 1/6. We add in 1/2. That's 4/6 or 2/3. And we get 0.66666. I'm going a little fast here. You can plug the numbers in, do it mathematically if you want. So again, a little bit of rounding error, but we have our P and our Q value. Okay, now, here's the alternative method. This is the one I prefer, but whichever you like. With this value, we can actually skip the genotype frequencies that we have calculated. All I want to do if I figure out my allele frequency is add up all of the big A alleles represented in my sample, add up all the little a alleles, and then divide by the total. So to get all of my big A's, I'm going to do 2 times 40, which represents the individuals that carry 2 copies of that allele. And then I'm going to add in my heterozygotes that only carry 1 copy of that big A allele. And I get a value of 80 plus 80, or 160. So I have 160 big A alleles in this population. Now, it's not a frequency yet. To get to a frequency, we need to divide by the total. So let's do our little a alleles, same way. Add in the individuals that carry 1 copy. And so we are now going to have a total of 240 plus 80, or 320 little a alleles. To get our frequencies, all we need to do is divide by the total. So we have 480 total alleles. And you'll get the same result that we got last time. 1/3, or 0.33333, are big A's, and then 2/3, or 0.66666, are little a's. So we now have our frequencies. Now, to figure if this population is in Hardy-Weinberg, all we need to do is plug it into the equation. So remember, p squared plus 2pq plus q squared is always going to equal 1. And each of these individual components of the equation, let's make this so it looks like a mathematical equation. Each of those individual components of the equation represents a different part of the population. This represents the predicted value for the homozygous dominant, the predicted value for the heterozygotes, and the predicted value for the homozygous recessive. So we just simply plug our values into this equation. And so I'm going to have 0.333, or 1/3 squared, plus 2 times 0.333 times 0.6666. And then we're going to add in our Q value, which in this case is 0.6666, like that. And that's always going to equal 1. Right? So we're not testing whether or not that equals 1. That's a common mistake. As long as we've done everything correctly, it will always equal 1. What we are testing is whether these predictions, and I need to do this superscript, I forgot to put my squared value there, so superscript, okay. So what we're testing is whether or not these values match our original observations, okay? So I'm going to need the calculator for this one. I don't know about you guys, but oops, let's clear that. So 0.3333 squared. Again, we got a little bit of rounding error here, but it's roughly 11% or 0.011. So go down to the next one. Okay, roughly again. We'll have some rounding error, but given that rounding error, or not accounting for that rounding error, these all should equal 1. So here I have 0.33 times 2, which is 0.66. So I'm getting 0.66 times 0.66. So let's do that one. Okay, so roughly 44%, or 0.44%. Sorry, 0.44 is the frequency. Same thing here. We're going to do 0.666 squared, right? Which, remember, we just did, so we already know that's 0.44. And again, we say that that should equal 1. So we're predicting 11%, 44%, 44%, that's 88 plus 11. We're short 1% because of rounding error, but that's all right. We're close enough, and we could represent this with more digits here, but we're okay for what we need to do. So now we are going to compare each of these. We predict that 11% of the population should be homozygous dominant, but we have 40 out of a total of 240. Right? So we already know that it's 16% because I made you calculate that already up here. So we predicted it 11%, but in reality we have 16%. We predict 44%, but in reality we only have 33%. We predict 44%, but we actually have 50%. So this is not in Hardy-Weinberg equilibrium. Okay? So assuming evolutionary forces stay the same, what would we expect the genotype frequencies to in the next generation to be? And if there is some, this is a little bit difficult to predict. So for this answer, I'm going to show you some of the options. So if these evolutionary forces are continuous, then we might expect to see the same values. We can have an evolutionary force that keeps a population out of Hardy-Weinberg equilibrium, but is constant, so that basically we have balanced evolutionary forces versus the forces that are trying to bring it back in. So we would expect it either to stay the same, or if there's a strong evolutionary force that's continuing to move it in one direction, we may expect it to continue to move in that direction. So, or it could change, and the type of change will help indicate what type of evolutionary force is acting on this population. Okay, so this is a little bit tricky, but it's kind of one of those interesting things for biologists, because if they can continue to watch this over many generations, they may be able to see some interesting things going on that then they may be able to connect to one of the environmental or evolutionary forces on this population. Okay, I'm gonna, excuse me, I'm gonna allow you to do number 2 the same way. Okay, so walk through it. Should be pretty straightforward for these first 3 parts. This last part, remember, if it's in Hardy-Weinberg equilibrium, then you would expect it to stay at Hardy-Weinberg equilibrium unless there's some change. But we're asking here what would happen if those evolutionary forces remain unchanged. So if it's in Hardy-Weinberg equilibrium, then they would just remain unchanged. All right, so now Let's look at a third one. Now, I purposely made this one very easy. It's an example we used in class several times. You should be able to do it really, really rapidly. It's just your standard 0.5 for big A allele, 0.5 for little a allele. Everything's in Hardy-Weinberg equilibrium. So we'll run through that, just confirm it. Hopefully you're very comfortable with that. But what we are going to do is follow up with that. I want to spend a little bit more time helping you through this follow-up. So now we are going to assume that for this gene above, that it is a gene that determines the color of these flowers. And it does so in an incomplete dominant pattern, so that the big A individuals, represented here, have red flowers. The big A, little a, represented here, have pink flowers, and the little a have white flowers. And I've put the genotype counts here just for reference. That's our first generation that we measured. Now, if there's a change in the pollinators, so that a hoverfly pollinates only these red flowers, so red flowers will only be able to mate with red flowers, a bee pollinates with only the pink flowers, and a moth pollinates only the white flowers, then what would we expect to happen? So we've introduced an evolutionary force. We've introduced some non-random mating. And it's a bit of an extreme example, but it's purposely that way so we can see the effects. So we can do this mathematically. I think it's easier for most students to just kind of reason through it. So let's think about what would happen. In generation number 2, all of these individuals, when they reproduced, they would make only red flowers, right? Big A mated with big A can only make big A offspring or red flowered offspring. So assuming that they, for all other intents and purposes, are competing equally with these guys, they would basically represent themselves again in the next generation. So we would have about 250 individuals that would be red flowers. Now, white flowers mating with white flowers, little a, same thing. They can only make other white flowers. However, we have this interesting condition when a pink flower mates with a pink flower. And you may remember back to Bio 1 or Bio 2 when you did genetics and you learned about Punnett squares. And one of the most common Punnett squares they do is a cross between two heterozygotes. What happens when a big A little a mates with another big A little a? And I won't run you through all the details, but basically half of the offspring are just like mom and dad. So about 250 of the resulting offspring would look like mom and dad, big A little a, they would be pink. However, a quarter of the offspring are big A paired with big A. So in this case, about 125 of these would be big A, which would put them over here. Right, big A, red flowers. So in total, we'd have about 375 red flowers, 2/3 of which came from the red flowers mating with red flowers, and 1/3 of which came from mating with pink flowers. And then, of course, we'd have a quarter of this population, or 125, that would produce white flowers. So over here, we add in those 125 individuals, and we get 375. So we have gone from a balanced Hardy-Weinberg equation to one that is at imbalance. And interestingly enough, if you go through and figure out, if you take these new genotype counts in generation number 2, 375, 375, and 250, you're going to get the same allele frequencies. You're going to get a p-value of 0.5 and a q-value of 0.5. However, because of the non-random mating, this is demonstrating this imbalance. Now, a follow-up question here, and actually I don't know why, but I don't have the follow-up question here. Oh, there it is. What would you expect the genotype frequencies to be in? Oh, no, let's put in a follow-up question. I'll post this new version so you can work on this new one. In fact, let's make this question number 6. There we go. So the follow-up is, what? I'm putting that in the wrong place. Bear with me. Word thinks that it knows everything I want to do, but half the time it's wrong. Okay. I gotta put, oh, there we go. Okay. So, what is the long-term outcome if this type of pollination persists? Okay, so each generation, when red mates with red, they're going to represent themselves in the population. White, same thing. But when pink mates with pink, they lose half of the resulting offspring to the other phenotypes. A quarter of the resulting offspring go over here, a quarter of them go over here. And if that process continues generation after generation, then eventually the pink flowers will be very, very rare and eventually would go extinct. So this sort of assortative mating, right, that's a type of non-random mating where like mates with like individuals, could result in a speciation events. So the long-term outcome is going to be continued loss of pink flowers and eventual segregation of the population into two distinct types, white and red. Now, originally, when this occurred, they may even still be nearly genetically identical, except for this one segregating site, this one gene that we've put all of the red alleles in one part of the population and all the white alleles. But if that is a barrier to reproduction, then eventually, given time, differences will build up in those populations and they'll become two distinct species. So this type of assortative mating can be a force that influences and perhaps even drives speciation events. Okay, so make that blue so it's a little easier to distinguish from the question. All right, so problem 6. Let's give it some more space here. Sometimes I wonder about Word. Anyway, I'll fix it and I'll post it later. Problem number 6 is now assume the gene above determines the color of flowers, but now in a classic dominant recessive pattern, right? So we have a little bit different genetics here going on. So I want you to do this and do the same thing. Now, the original pollinator for the pink flower is no longer a factor. So in this example, we said the bee is no longer a pollinator for the species, and they may go extinct if they needed those pink flowers. More likely they would adapt and move to other species or take advantage of different resources in the population. But now we're left with only two pollinators, the pollinator of the red flowers and the pollinator of the white flowers. Okay, so I'd like you to go through and figure out what would happen in this instance. Okay, it's a little tricky. Again, if you struggle with it, use this example, go back over this one. Now try to think for each of these populations what would happen. You already know what would happen for the white ones, right? That's pretty straightforward. White only mates with white, that's easy. But what happens when big A mate with big A, or big A little a? There's going to be a variety of matings here, okay? So on average, about a quarter of all matings are going to be the offspring of these guys, and 2/3 of all mating, or sorry, 3/4 of all matings are going to be the resulting of these matings. So go through and work that out and see if you could come up with some predictions. Okay? Now, the last step that we are going to do for this is to say, what would happen if we had the same setup as number 6, but now one of the pollinators is no longer available. And so in theory, the white flowers are never going to be able to reproduce because they no longer have a pollinator. Okay? So what happens, we still have little a alleles represented in these 500 individuals who are heterozygotes. What happens to that little a allele in generation number 2, and then maybe even think about what would happen over subsequent generations. Okay, so this follow-up question, if you are able to figure out that generation number 1, 2, and then kind of see the pattern, you will then be able to figure out and answer this follow-up question. So again, if you're having trouble, these are a little bit more advanced examples here at the last one. If you're having trouble getting through them, if you're not 100% certain of your answers, please log in to one of our regular Zoom sessions or come and see me. I guess come and see me via Zoom. That's kind of the new world that we live in. Good luck.